Hi everyone, welcome back. Today we'll be talking about arc length. I think it's one of the coolest topics in Math 104. The concept that we're able to determine exactly the length of the curve sitting in front of me, well, an arbitrary curve, I guess, using the calculus that we know so far is really fascinating to me. So what we're going to do here, as we always do with calculus, is chop this curve up into a bunch of small bits. And then we're going to connect those bits with a line, and we're going to see if this estimates the length of the curve very well when we sum them up. And what we can imagine is that we make these segments super close together. Like if I zoom in and make them like this, then we can get a very good approximation. And when we integrate, we get an exact length of the curve between the points A and B. So how do we do this? Well, we have to go back to our good old friend, the Pythagorean theorem. And so let's look, if we zoom in really close to this curve, say right here, I can zoom in and I have the curve that looks like this, and then I have a point here at maybe xy, and a point here at x plus delta x and y plus delta y. And I'm trying to estimate the length of that little portion of the curve using the distance between those 2 points. So this distance here then is delta x, this distance here is delta y, and we'll call this delta L, L being for length. Well, the Pythagorean theorem says that delta L is equal to the square root of delta x squared plus delta y squared. And in particular, I can divide out that delta x squared to simplify things. I'll get that delta L is equal to the square root of 1 plus delta y over delta x squared times delta x, so that delta x I can factor out, move outside of the square root as a single delta x. And then, as we know, if we get this precise enough, we can actually turn these into differentials, which would be dl is equal to the square root of 1 plus dy by dx squared dx. And that's going to give us very accurately the length of this curve here. And so all I need to do is sum them up over the course of the entire curve from a to b. We know exactly how to do that. So we integrate from a to b dl, which is the integral from a to b, the square root of 1 plus dy by dx squared dx. And then the only thing that changes is if you decide to use functions of x instead. So x is equal to sine of y, for instance. Then what you do is you switch the variables around and you get your length is the integral from c to d, the square root of 1 plus dx by dy squared dy. This is if y is going from c to d, and this one up here is if a is between, if x is between a and b. Okay, so depending on which variables you're given in the problem, you use either one of these forms, which are exactly identical, but switching the variables. So this looks really scary, right? This is a horrifying looking thing to integrate, but the examples we're given, we'll see that they actually simplify quite nicely using almost exactly the same trick. So let's do an example. Let's find the length of the curve y is equal to a third x cubed plus 1 over 4x between 1 and 8. So you're saying, Jimmy, I thought you said this was going to be easy, it was going to look good. Well, it will, you'll see. So essentially what I'm going to do is I'm just going to find what this integrand is step by step. So I'm going to take, we're using the other one, the one up top, but same thing. I'm going to take this integrand step by step here and essentially just work out dy by dx. I'm going to square it, I'm going to add 1, I'm going to hope I get a perfect square, and then I'm going to do the integral at the very last step. Okay, so dy by dx is equal to x squared minus 1 over 4x squared. If I square that, I get x to the 4th minus 2, 1 over 4x squared times x squared, and then I square that last term to get 1 over 16x to the 4th. What we'll notice here is that these x squareds will cancel out, and you're left with minus 2 times a quarter. So this term right here actually gives you minus a half. And that's pretty typical, honestly, of this problem, and we'll see why in a second. But if I add 1 to this, this becomes x to the fourth plus a half, right? So it's minus a half, I add 1, I get plus a half, plus 1 over 16 x to the fourth. And what's really weird, or what's seemingly coincidental, is that we end up getting a perfect square that's almost identical to the one we started with, but we're missing a minus sign. So this becomes x squared plus 1 over 4x squared squared. Okay, so we had a minus sign starting out here. We now have a plus sign. That's thanks to this additional 1 I added out front and some good math going on. Anyway, when I take the square root of this, which I need to differentiate, I simply just get x squared plus 1 over 4x squared. So then my length, this right here is dl, right? So my length is integrating that from 1 to 8, x squared plus 1 over 4x squared dx. And what's even more interesting is that we already did this in reverse, right? We took dy by dx and got that, so we're kind of going the opposite direction. We'll pop out the same thing with an additional minus sign. So we're going to get a third x cubed. This becomes minus 1 over 4x. Okay, that was it. I plug in 8, I plug in 1, which I don't feel like doing, and you will get your answer here. So again, it's this trick of this adding the 1 here that really makes your life easier, and I see it a lot going on. If that doesn't really happen, then you get a very simple expression. I've seen literally the dl element come out to just be 1. I've seen trig functions in there very rarely, but generally it's this scenario here. Let's do one more example, just so we get the hang of it. Let's do the curve natural log of x minus 1 over 8 x squared, and we're going from 1 to 2. So again, I'm just going to differentiate. I get 1 over x minus x over 4. I square that. I get 1 over x squared minus 2 times 1 over x times x over 4. And I add to that x squared over 16. Again, this becomes minus a half, so when I add 1 to it, I get 1 over x squared plus a half plus x squared over 16, which, as you guessed, this is a perfect square without the minus sign of this expression, which we've seen before. So when I take the square root of that, I'm simply left with 1 over x plus x over 4. And that again is our little length element dl. So what we're going to do is we're going to integrate that from 1 to 2. 1 over x plus x over 4 dx. Again, we're going to have that weird thing where we pop out natural log of x plus 1 over 8 x squared. And then you plug in 2 and 1, which I won't do, and get your answer. So, don't ever just, look at this and go right to here. That's probably not a good look. But, you can feel pretty confident if you pop out this minus 1/2 here that you're going to have a similar trajectory for all your